Welcome to Deep Dive Dialogues, where we make the complex simple and the simple fascinating. I'm your host, Isabel, and today we are diving into something that honestly made my brain do a little backflip when I first read the paper. We're talking about using large language models to clean up brain signal graphs, for real. And to help me unpack this, I have two of the sharpest minds in AI. First up, the man who can explain a transformer model using a recipe for bibimbap. JJ.
Hello, Isabel, and hello, everyone. It's good to be back. And I have to say, when I first saw this title, LLM as Clinical Graph Structure Refiner, I thought, okay, this is either going to be a gimmick or something genuinely clever. And after reading it, I think it's the latter.
Do it, and I'm Zheng, and I'm going to be the one who asks. Why? Why do we need a giant language model to fix a graph? Isn't that like using a sledgehammer to crack a nut? Or in this case, using a poet to edit a spreadsheet?
Okay, that is a perfect Jia opening salvo. And that is exactly the tension we're going to explore today. So let's set the stage. The problem is EEG signals. Those squiggly lines from your brain, they're incredibly noisy. And when you try to build a graph from them, connecting different brain regions, you get a mess. Redundant edges, irrelevant connections. It's like trying to find a clear path through a spider web that's been hit by a hurricane. So the paper's big idea is, what if we let an LLM look at those edges and say, nah, this one's noise. Keep this one. That one's important. JJ, from your perspective as a researcher who's worked on graph neural networks, is this a natural fit or a stretch?
It's a natural fit, but not for the reason most people think. See traditional graph construction methods. They're either statistical, like correlation, or they're purely learned, like a neural network predicting edges. Both are blind, they see numbers, they don't see context. An LLM, it can read a description of a node. It can understand that a certain brain region is responsible for visual processing and another for motor control. And it can reason. If these two are firing together during a seizure, that's meaningful. If they're firing together randomly, that's noise. It's not just pattern matching, it's contextual reasoning.
But here's my problem, and I say this as someone who has deployed models in clinical settings. The paper says the LLM acts as an edge set refiner. It makes decisions based on textual and statistical features of node pairs, but an LLM is a black box. It hallucinates, it has biases. Are we really comfortable letting a model that sometimes thinks 2 plus 2 equals 5 decide which brain connections are real? That feels risky.
That is a very valid point, Jia, and the paper actually addresses this indirectly. They use a two-stage framework. First, they build an initial graph using a transformer-based edge predictor. That's the statistical part. It assigns probability scores. Then the LLM comes in as a second opinion, a refiner, not a creator. So the LLM isn't building the graph from scratch. It's looking at a candidate set of edges and saying, this one passes the smell test, this one doesn't. It's more like a quality control inspector than a construction worker.
Exactly. And the results on the TUSZ dataset, the Temple University Seizure dataset, are compelling. They show that LLM-refined graphs not only improve seizure detection accuracy, but they also produce cleaner, more interpretable structures. The graph actually makes sense to a neurologist. That's huge. Because one of the biggest problems with deep learning in medicine is that doctors don't trust a model they can't understand. A cleaner graph, with meaningful connections. That's a bridge.
I'll concede that interpretability is a win, but I still worry about the cost. Running an LLM to refine edges, that's expensive and slow. In a real-time seizure monitoring scenario, every millisecond counts. Is this practical, or is it just a cool academic exercise?
That's the million-dollar question, and I think the answer is, it depends on the use case. For offline analysis, for research, this is fantastic. You get a cleaner, more trustworthy graph. For real-time monitoring, maybe not yet, but the paper is a proof of concept. It shows the direction. And honestly, the idea of using an LLM not as a chatbot but as a structural reasoning tool, that's a paradigm shift. It's like using a chef to organize your pantry instead of just to cook a meal.
I agree, and I'd add that the cost is dropping fast. Smaller, specialized LLMs, distilled models, they can do this kind of reasoning for a fraction of the cost, so in 2 years this could be standard practice. The key insight here is that LLMs understand relationships, not just statistical relationships, but semantic ones, and in a field like neurology where the data is messy and the stakes are high. That semantic understanding is gold.
Okay, I'm not fully sold on the deployment side, but I am sold on the research direction. Using LLMs as graph refiners, it's creative, it's thinking outside the box, and I appreciate that they didn't just throw an LLM at the problem and hope for the best. They built a structured pipeline. That's good engineering. So, for now, I'll call it a promising start, but I want to see replication studies, and I want to see a cost-benefit analysis for real clinical workflows.
Fair, very fair. And that is exactly the kind of critical optimism we need in this field. So to wrap up, we've got a paper that takes the noisy, messy world of EEG signals, uses a smart two-stage pipeline with a transformer and an LLM, and produces cleaner, more interpretable graphs that actually help detect seizures. It's not perfect. It's not ready for the ER tomorrow, but it's a brilliant step forward. Thank you both for this conversation. JJ Jiayang. Always a pleasure.
Thank you, Isabel. Always fun to untangle a knotty problem.
Do it, and thank you to the viewers for sticking with us through the brain waves. Keep asking the hard questions.
Channel everyone. Thank you.